we shall look at the criteria for exactness, that is a necessary and sufficient condition for an equation to be exact, and look at some of the examples and how to solve such types of equations. So let's start with exact differential equations. Now we know already that general solution, say yx, of a first order differential equation is often implicitly defined as a function of x and y. So it is defined as fxyx is equal to c. Okay, so such an implicit equation usually gives a general solution of a first order differential equation. Here c is a constant. Okay, so now suppose if we are given such kind of an identity, we can get the original differential equation by differentiating both sides with respect to x, right? So if suppose this equation implicitly defines y as a differentiable function of x, we can get the original differential equation. So we get the original differential equation in this form: del f over del x by partially differentiating, so plus del f over del y into dy over dx is equal to 0. So we differentiate both sides with respect to x, and we get the original differential equation is in this form. Now if I consider this partial derivative with respect to x, so the notation is fx of xy. This is for del f over del x, and the partial derivative del f over del y, this is denoted by fy of xy. So if I consider this function as m of xy and this as n of xy, so I can write the above equation as mxy plus nxy dy over dx is equal to 0. So it is convenient to write the above equation as mxy dx plus nxy dy is equal to 0, and this is called the differential form of the above equation. Say 1. This is the differential form of 1. So now a general differential equation, say y dash, that is dy over dx is equal to fxy. This can be written in this form by taking mxy is equal to fxy and nxy as minus 1, right? So the above discussion shows that if there exists a function, say fxy, okay, if there exists such a function fxy such that the partial derivative of f with respect to x is m and partial derivative of f with respect to y is n, then the equation fxy is equal to c implicitly defines a general solution of the equation given by star, right? And now in this case the equation given by star is called as an exact differential equation. So basically, if there exists a function fxy such that the partial derivative of f with respect to x is nothing but m, this function, and the partial derivative of f with respect to y is nxy, then we call this such an equation in this form as an exact differential equation. So let us see some of the examples and then the criteria. So consider the differential equation y cube dx plus 3 xy squared dy is equal to 0. And consider the function fxy as xy cube. Okay, so the partial derivative of f with respect to x is equal to y cube, and the partial derivative of f with respect to y is 3xy square. And so this is equal to mxy, and this is equal to nxy, and hence there exists a function satisfying the definition of exactness. So the above equation is exact. Now similarly, consider another example. Example number 2. So consider the equation 2x plus 3y dx plus 3x plus 2y dy is equal to 0. So now consider the function fxy as x squared plus 3xy plus y squared. So now again fx of xy, so this is equal to 2x plus 3y, and this is equal to mxy, and fy of xy is equal to 3x plus 2y, which is equal to nxy, and hence again the necessary condition is being satisfied, so the equation is exact. So far we have only seen a necessary condition to check the exactness of a differential equation. Now let us look at a criteria for exactness that gives a necessary as well as a sufficient condition to check whether an equation is exact or not. So suppose that the functions mxy and nxy, these are continuous and have continuous first order partial derivatives in an open rectangle. Okay, so these functions, first of all, they are continuous, and secondly their first order partial derivatives are also continuous. That is, if we consider m, that is del m over del x and del m over del y and del n over del x and del n over del y, so these are also continuous in some open rectangle where x lies between a and b and y lies between c and d. So then this differential equation m dx plus n dy is equal to 0. This is exact if and only if the partial derivative of m with respect to y equals the partial derivative of n with respect to x at each point of this rectangle R. Okay, so for all x in AB and y in CD, so this condition should hold, that is del m over del y is equal to del n over del x. So then the equation would be exact. This is an if and only if condition. So to check whether this kind of equation is exact, you just have to check that this condition given by star holds for all points in this rectangle. So let us see an example. So we are given the differential equation 6x y minus y cube times dx plus 4y plus 3x squared minus 3x y squared dy. This is equal to 0. Now let us check the exactness. So here mxy, this is equal to 6xy minus y cube, and nxy, this is equal to 4y plus 3x squared minus 3xy squared. So now let us see del m over del y. So this is equal to 6x minus 3y squared, right? And which is equal to del n over del x. Okay, so if you partially differentiate this with respect to x, what we get? We get 6x from here, 0 from here, and minus 3y squared from here. So these two are equal. So these are equal for all x comma y in R2, right? Now we integrate del f over del x is equal to mxy. So we integrate this equation with respect to x. Okay, and we get fxy is equal to integration of 6xy minus y cube dx. So after integration we get 3x squared y minus xy cube plus gy. So because we are integrating with respect to x, so we are treating y as a constant. So this for the constant term, a function of y would be added. Okay, not only a constant, because we are integrating with respect to x. So now we differentiate with respect to y. Okay, so we have got fxy is equal to 3x squared y minus xy cube plus gy. Now we differentiate with respect to y. Okay, and we had del f over del y is equal to nxy. So let's see what we get as nxy. So nxy is equal to, so del f over del y, 3x squared minus 3xy squared plus g dash y, right? And we are already given nxy was what? This was equal to 4y from here plus 3x squared minus 3xy squared. So this term is same and these terms are same. So from here we get g dash y is equal to 4y, and integrate this to get gy is equal to 2y squared plus c1. So here c1 is an arbitrary constant independent of x and y, and hence we get fxy as 3x squared y minus xy cubed plus 2y squared plus c1. So this is the solution, general solution of the differential equation, or an implicit solution can be written as 3x squared y minus xy cube plus 2y squared is equal to c. So this is an implicit solution of the given differential equation. So here we have absorbed the constant c1 into the new constant c. So this is how we solve an exact differential equation.